All right, let's dive into the world of telescopes. We're exploring Chapter 6, Optical Instruments, by Professor Ramesh Dangana today.
It's fascinating how these tools reveal the universe's secrets.
Yeah, before telescopes, we were limited to just our eyes.
Right, but telescopes extend our vision so much further. They're like super-powered eyes, seeing objects billions of light years away.
Mind-blowing. How do they actually work? What's the secret?
The secret is based on two principles of light: reflection and refraction.
Reflection like a mirror.
Exactly. Light bounces off the surface. Refraction is different. It's light bending as it passes between mediums like air and water.
Oh, like a straw looking bent in a glass of water.
Perfect. Telescopes use both, sometimes together, to gather and focus light from distant stars and galaxies.
So these instruments that see light years away rely on simple light bending and bouncing.
It sounds simple, but the way telescopes use light is precise and powerful. Refracting telescopes, for example, use lenses.
Lenses like in eyeglasses.
Exactly. Specifically, a convex lens, like a magnifying glass. It bends light rays to converge at a focal point.
So the lens takes light rays from a star and focuses them into a tiny point.
Precisely. And that's where the star's image starts to form. But to see it, we magnify it with the eyepiece lens.
That's like a second magnifying glass, enlarging the image further.
Exactly. And the magnification level depends on the focal lengths of both lenses. Magnifying power is the ratio of those focal lengths.
Wait, can you explain focal length?
Sure, it's the distance between the lens and the focal point where light rays converge.
So a bigger difference between focal lengths means higher magnification.
Exactly. But there's more to telescopes than magnification. We also need to consider how much light they collect.
Right, because more light means seeing fainter objects.
Exactly. The objective lens is like a light bucket, and bigger means gathering more light. This is key for seeing faint, faraway objects.
So bigger lens equals more light equals seeing more of the universe. But is there a limit to lens size?
That's where things get interesting. There are limits to how large we can make a single lens. Plus, there's angular resolution, which affects detail.
Angular resolution, I've heard of that.
It's the ability to distinguish two closely spaced objects. Imagine observing two close stars. High angular resolution shows them separately. Low resolution might show a single blurry blob.
So to see fine details in galaxies, you need high angular resolution.
Absolutely. Generally, larger telescopes have better angular resolution, but even then there's a limit due to the nature of light.
Because of how light behaves.
Exactly. That's where interferometry comes in.
Interferometry is like combining multiple telescopes into one giant telescope, right?
Yes. By linking telescopes, we create a virtual telescope with a much larger diameter, increasing angular resolution for incredible detail.
It's like having a telescope the size of a city.
Precisely. And that's just one way astronomers are pushing the limits of telescopes.
Fascinating. From basic light principles to these advancements, telescopes open our eyes to the universe's vastness.
They truly do. And as technology evolves, who knows what discoveries await us?
You know, it's really amazing how those simple light principles are driving our exploration of the universe.
Yeah, and when you see those complex images from telescopes, it really makes you appreciate how clever these instruments are.
Absolutely. We've talked about lenses, focal lengths, and magnification. But I'm still a bit confused about how the light the objective lens collects turns into an image.
That's where image formation comes in. Remember how we talked about the objective lens converging light rays at the focal point?
Yeah, that's where the light from far away meets, right?
Exactly. But it's more than just a point of light. Think of it this way. Every point on a distant object, like a star, a planet, or even a whole galaxy, is emitting light. The objective lens takes all those rays and sends them to matching points on a plane called the focal plane.
So each tiny point on the object has a little point of light on that focal plane.
Exactly. And all those focused light points on the focal plane create a real but upside-down image of the object.
Wait, upside down, you mean the image is flipped?
Yes. But the eyepiece lens flips the image right side up again before we see it.
Oh, that's neat. So it's flipped twice, once by the objective lens, then back again by the eyepiece. But how much detail can we really see?
That brings us back to angular resolution, which we talked about earlier. Remember, it's the ability to distinguish between two objects that are close together.
Like seeing two stars as two separate points of light instead of one blurry mess.
Exactly. And here's where it gets even cooler. Angular resolution isn't just about the telescope's size. The wavelength of light is really important too.
Wavelength. So now we're talking about the physics of light.
We are. The shorter the wavelength of light, the better the angular resolution could be. That's why astronomers use telescopes that see in more than just visible light. They use the whole electromagnetic spectrum.
You mean there are telescopes that can see infrared light, ultraviolet light, even X-rays?
Absolutely. Observing these different wavelengths gives astronomers a more complete picture. Infrared light, for example, can see through clouds of gas and dust, while X-ray telescopes can study black holes and supernovae.
It's like having different ways of seeing the universe, each giving unique information.
Exactly. And while each type of telescope is great, a single telescope still has limits, even when looking at different wavelengths. That's why interferometry is so important.
Right. Combining the power of multiple telescopes basically creates a giant virtual telescope.
You got it. And the bigger the virtual diameter, the better the angular resolution, letting us see finer details.
It's like a superpowered zoom for the universe.
You could say that. It's a game changer that pushes what we can observe.
It's mind-blowing. It's amazing how what we know about light and optics has led to these advancements in astronomy.
It really is. And as technology keeps getting better, we can only imagine what we'll discover next.
I can't wait. But maybe we should step back and think about the impact these discoveries have had.
That's a good idea. What has stood out to you about how telescopes have changed our understanding of the universe?
Yeah, it really is amazing how telescopes haven't just given us more knowledge about the universe. They've actually, changed how we see our place in it.
Absolutely. Right from the start, telescopes have pushed the limits of what we know and can see.
Think about those first astronomers, like Galileo. His observations with the telescope were revolutionary, right?
Yeah, definitely. When Galileo looked at Jupiter with his telescope and saw its 4 biggest moons going around it, it really challenged the idea that everything revolved around the Earth.
You mean that geocentric model?
Exactly. Seeing those moons clearly orbiting Jupiter supported the idea that the sun was at the center of the solar system.
That must have blown people's minds. It's like our view of the cosmos totally changed overnight.
It was a big shift. And that was just the start of what telescopes have shown us.
So besides proving that the Earth wasn't the center of everything, what other discoveries did telescopes make possible?
Well, telescopes let us study the planets and moons in our own solar system in detail. We learned about what they're made of, their atmospheres, their weather, even their internal structures.
It's like we got a backstage pass to the solar system.
I like that. And as telescopes improved, we could see even further into space.
Which led to finding galaxies beyond our own Milky Way.
Right. In the early 1900s, Edwin Hubble used the Hooker telescope and realized those fuzzy patches of light were actually entire galaxies, each with billions of stars.
So our Milky Way is just one of so many galaxies out there in the vastness of space.
That's right. And the discoveries haven't stopped. Modern telescopes with their advanced tech have opened up even more possibilities for observation.
I've heard about telescopes that see infrared light, so they can look through gas and dust and see things hidden from visible light.
Yeah, infrared astronomy has been huge for understanding how stars form, planetary systems, and how galaxies evolve. Then there are X-ray telescopes that study black holes and supernovae.
It's like we have a whole new set of senses for exploring the universe, each revealing something different.
It really is. And with each new telescope, we keep pushing the limits of what we can see and understand.
It's exciting to think about what we'll discover next. From those first views of Jupiter's moons to those amazing images from today's space telescopes, these instruments have been key to our understanding of the cosmos.
Absolutely. It shows human ingenuity and our endless curiosity about the universe.
So everyone listening, keep looking up at the stars, keep asking those big questions, and keep exploring. Until next time.